Again, we have a situation with the ball being thrown from position S to home plate. The coordinate system is given to us. The origin is at home plate, up is positive, to the left is positive, as indicated by my blue arrows. And the first thing we're looking for is the horizontal velocity, I'll call that v sub x, versus time. The ball starts out, it has a certain velocity in the x direction. On the way up, it has the same velocity in the x direction. At the top of its peak, it has the same velocity in the x direction. That never changes. So the velocity in the x direction is constant, and it's always positive. So that corresponds to A. The acceleration in the x direction versus time. Well, because we know that this object is in free fall, we're ignoring air resistance. Nothing is pushing on the ball in the x direction. So the acceleration versus time is 0. That corresponds to C. We can also look at the velocity versus time curve. The slope is 0 everywhere, so the acceleration would be 0 everywhere. In the y direction, what does our velocity look like? Well, it starts out with a big velocity in the y direction, and that gets smaller, and it goes to 0, and then it starts to go in the other direction, and it gets bigger and bigger in the other direction as the ball comes down towards home plate. So let's just fill in a few things. We know it starts off large and in the positive direction. We know it's 0 somewhere in the middle, and we know it's large in the negative direction right before it hits home plate. And we'll connect those with a straight line. So this is the v sub y versus t graph. That corresponds to I. The acceleration in the y direction versus t, well, we know what that is. It's 9.8 meters per second squared in the downward direction, which is the negative direction. It's constant and negative, so that looks like graph B. And I know they only asked for 4 items, but why don't you pause the video and see if you can plot these last 2. The horizontal position versus time, x versus time, and the vertical position versus time, y versus time. All right, let's take a look at x versus time. So where does our object start out? At some large negative number, and as time goes on, the ball gets closer and closer and closer to 0, home plate. So I'm going to put those points on my graph. It starts off with a negative number, and as time goes on, it gets to 0. And because the velocity is constant, I know that's going to be a straight line. Now, the y direction, the ball starts out at 0, and it ends up at 0 back at home plate. But somewhere in the middle, it hits a peak. The question is, how do we connect those dots? Those dots were fairly easy to find. How do we connect them? You might be tempted to draw this curve. If y versus t looks like this, with linear paths connecting those dots, then what is the velocity in the y direction going to look like? The velocity in the y direction would look like this. It would have a positive slope and constant for the first half, and it would have a negative slope and constant for the second half. I'm looking at the y versus t curve now when I say slope. So if the slope is positive of the y versus t curve and constant, then our velocity is constant positive number, and on the other part, it's a negative constant. And is that what happens? Is the velocity in the y direction constant all the way up, and then it abruptly changes to a negative value and it's constant all the way down? No. I'm going to put a big red X through that. The v sub y versus t curve would not be correct if we chose a linear path connecting those dots for our y versus t curve. So let's go back and fill in what it should look like. It should be a parabola. And that's not listed on page 71.